part you see isn't the scariest. Above the water, the structure's so massive that when you stand beneath it, you can't see the top, shining brightly in the middle of the ocean. Impressive. But that's just the visible part. Below the water is what really keeps it all standing. Massive, submerged holes, steel pillars as wide as a house, and a system that can change the buoyancy of the entire structure simply by pumping water in or out. This is why it doesn't sink in storms. Not because it's heavy, but because it's designed so that storms can't reach the most crucial part. But building this thing is one thing, getting it out into the ocean is another, and keeping it stationary long enough to drill through the Earth's bottom, that's the story You Can Do will tell today. From shipyard to the ocean floor, this is the journey of the world's largest super drilling rig. This is not just a ship, it is a floating city navigating the extremes of the ocean. The Deepwater Titan, a masterpiece of deep-sea extraction, represents the absolute peak of modern energy engineering. Costing over $1 billion, this structure is a complex integration of tens of thousands of tons of steel and high-level automated systems. At first glance, it appears as a static metal giant amidst the waves. However, deep beneath the surface, its ballast and dynamic positioning systems operate continuously. It does not simply endure the crushing pressure of thousands of meters of water, it actively challenges the ocean's volatility to keep its drill bit perfectly still. This is the pinnacle of engineering precision, where human ingenuity confronts the raw power of nature. When night falls over the Blue Whale 1, the industrial scale becomes even more intimidating. It feels less like a platform and more like a high-tech fortress. As the sun sets, we witness the true scale of this Leviathan. Against the horizon, its silhouette dominates the seascape, dwarfing everything around it. This is a machine designed to be indestructible, a testament to the fact that we no longer just visit the ocean, we occupy it. This isn't just construction. It is a permanent mark on the map of deepwater exploration. If the Titan and Blue Whale are our outposts, the Appomattox is our monument. To understand how we move from occupying the sea to conquering it, we must look at how such giants are birthed. The Appomattox platform is essentially a skyscraper built on water, defying every logical constraint of construction. To build it, engineers had to move beyond traditional shipbuilding and adopt a logic of large-scale architecture. Imagine lifting a 29-story steel tower, weighing more than an aircraft carrier, and placing it onto a floating foundation that must remain perfectly level amidst the brutal swells of the Gulf of Mexico. This requires a level of structural engineering that pushes the absolute limits of integrity. Every joint, every weld, and every bolt is stress-tested against oceanic forces that would tear a standard vessel apart. It is a grueling, multi-year process where the goal is not merely to build, but to create a permanent, self-sustaining industrial ecosystem in one of the most hostile environments on the planet. From the shipyard in South Korea to its 7,000-foot deep operational home, the project acts as a giant 3D puzzle where 10,000-ton modules are stacked with inch-perfect precision. Beyond mere size, Appomattox represents a fundamental shift in sustainability. By adopting a fully electric design, inspired by the optimization of modern electric vehicles, the platform slashes emissions by 25%. The ingenuity extends to the deep-sea cooling systems, where researchers sourced water from 2,000 feet down, avoiding sensitive ecosystems while maintaining efficiency. Even the materials tell a story of innovation. From pipe insulation derived from medical-grade catalysts, to modular, extractable tanks designed to outlast corrosive chemicals for 4 decades. Appomattox is more than just an oil platform. It is a masterpiece of modern endurance. It stands as a testament to what happens when human ambition refuses to be limited by the depth of the ocean, successfully bridging the gap between cutting-edge technology and the raw, unforgiving power of the sea. But even the most perfect design is merely a theory until it is tested by the ocean's wrath. For the Appomattox, the ultimate exam began before it even reached its destination. What happens when the most advanced engineering meets the most violent force on Earth? The journey of the Appomattox from South Korea to the Gulf of Mexico was not just a delivery, it was a brutal test of design. Faced with the path of Super Typhoon Nauru, the team faced a multi-million-dollar dilemma: stay and risk destruction, or attempt a high-stakes race against the storm. The survival of such a structure relies on its semi-submersible design. Unlike a conventional ship that sits on the water's surface, a semi-submersible is engineered to be partially submerged. By allowing the lower hull, the pontoons, to sit deep underwater, the platform minimizes the surface area exposed to wind and wave action. It is a calculated, rhythmic dance between weight and buoyancy. This stability is rooted in the interplay of two physical principles: Archimedes' principle and the center of gravity. Because the massive, heavy pontoons are located deep beneath the surface, they act as a ballast, keeping the center of gravity low and stable. While a traditional ship's hull sits high and is tossed around by surface turbulence, the semi-submersible structure remains anchored in the calmer, deeper water. The waves may crash violently against the surface, but the legs of the platform allow the force to pass through or beneath it rather than against it. During the journey, this geometry was the only thing keeping the hull from disaster. It is a violent, terrifying yet awe-inspiring demonstration of why engineers spend years perfecting these designs. Whether navigating the Cape of Good Hope's 30-foot swells or outrunning catastrophic hurricanes like Harvey, the Appomattox proves that when human ingenuity respects the raw power of the ocean, we can build structures capable of surviving the absolute worst the planet can throw at them. To bring a structure weighing tens of thousands of tons to life, you cannot rely on standard construction tools. At fabrication yards like Hidromar Group, the scale of operations is industrial grade. This is not merely an assembly site. It is a cradle for structures capable of enduring the most punishing ocean environments on Earth. Every square meter of steel processed here is engineered to withstand the crushing pressure of the deep sea. We are talking about a facility that manages complex, multi-year projects where the margin for error is essentially non-existent. When you look at the sheer size of the gantries and the flow of the material, you realize this isn't just manufacturing. It is the systematic creation of a sovereign industrial entity that will eventually survive independently in the middle of a vast, turbulent ocean. Before a single piece of steel is cut, thousands of engineering hours are poured into the blueprint. The engineers here aren't just welding metal. They are simulating complex environmental stress tests. They model how the structure will flex, expand under extreme heat, and resist relentless saltwater corrosion over decades of service. This is where abstract mathematical models are transformed into the physical reality of a gargantuan machine. Every single rivet, every reinforced bulkhead, and every electrical conduit is plotted with a level of rigor that reminds you, this machine is not built for luxury. It is built for survival in the most hostile environment on our planet. It is a fusion of pure physics and heavy-duty mechanical audacity. Within the shipyard, the process moves from digital simulation to the tangible, industrial dance of fabrication. Massive steel plates are precisely cut and shaped, then joined by skilled welders whose work undergoes rigorous non-destructive testing. As the pontoons take shape, hollow, pressurized chambers designed to defy the crushing depths through the elegant application of Archimedes' principle, the structure begins to assert its own gravity. It is a laboratory of endurance, where human ingenuity is forged into steel, preparing these leviathans to stand unmoved against the violent, unforgiving rhythms of the open sea. When an offshore rig requires an upgrade, you cannot simply tow it into a standard harbor. The FPSO mooring system is the primary example of this logistical and engineering challenge. These components are the critical lifelines. They are the anchors that keep a multi-billion-dollar asset stationary against the constant, unrelenting pull of massive ocean currents. Replacing or repairing these mooring arrays demands millimeter-level precision. You are dealing with massive steel chains, specialized winches, and hydraulic tensioners, components that must remain flawlessly operational in freezing, corrosive, and high-pressure conditions. A single failed link in this system does not just mean a delay. It could turn a billion-dollar production platform into a drifting liability. At the Hidromar Group's yards, this retrofit process is a masterclass in maritime life extension. It begins with high-fidelity 3D scanning and structural modeling, where engineers simulate the fatigue and stress loads that these anchors will face over the next decade. The transition from the digital model to the shipyard floor is where the real audacity lies. Installing suction piles and complex tensioning systems requires perfect synchronization between heavy-lift cranes and specialized divers or remote-operated vehicles. This project isn't just about fixing broken parts. It is about restoring the structural integrity of a vessel that operates at the very limits of human reach, ensuring that our offshore energy infrastructure remains anchored against the raw, indifferent power of the deep sea. Watch the automated plasma cutters and welding columns in action, and you realize the stark difference between standard manufacturing and offshore engineering. This is a battle of density and durability. Ultra-high-strength steel plates are rolled under immense hydraulic pressure to form the thick, curved walls of the pontoons. If a weld fails under the pressure of 3,000 meters of water, the result is catastrophic. This is why the fabrication process is slowed down to a crawl, not because of inefficiency, but because every single centimeter of that bond must be perfect. sometimes, the greatest challenge in industrial engineering is not just casting a massive block of steel, but mastering the art of precision turning it. These giant bollards, essential anchors for subsea pipelines, require heavy-duty, large-scale lathes capable of sub-micrometer accuracy. Every surface must reach absolute perfection. Even a microscopic deviation risks catastrophic failure under immense hydrostatic pressure. Maneuvering such immense weight requires specialized heavy-lift transporters and synchronized crane operations, where the slightest movement must be perfectly calculated to prevent structural stress. This project exemplifies offshore engineering. Delicate positioning on the seafloor carries the burden of billion-dollar assets. The Ayatzil Sea Jacket launch represents a triumph of precision logistics and coordinated teamwork. After mobilizing from Mississippi to the Mexican offshore site, the project required flawless communication to maneuver the transport vessel and secure the 7,000-ton structure. Through intense overnight preparations, ballasting to a precise 3.75-degree angle, the team successfully executed the launch at dawn. Installing such a massive jacket into 400 feet of water is a monumental feat, proving that when safety, expert engineering, and dedicated personnel align, even the most complex offshore operations become seamless. Finally, we place the finishing pieces into the puzzle, the assembly of the massive topside modules. From a distance, this may appear to be a chaotic industrial site, but in reality, it operates with the precise coordination of a Swiss watch. Each module is not merely a cluster of steel. It is a self-contained, high-tech factory, packed with intricate piping networks, electrical grids, and complex central control computers. Lifting and mating thousands of tons of steel onto the support jacket with near-zero tolerance is the absolute pinnacle of process management. Every cable must connect. Every fluid line must seal perfectly upon the very first contact. In this yard, the pace never slows down, and the level of precision is not just a preference, it is a non-negotiable requirement for existence. This is why, when you look at this process, you don't just see heavy machinery. You witness a sophisticated, high-level engineering philosophy operating in perfect, synchronized harmony. As these modules hover in the air, suspended by gargantuan cranes, the true complexity of offshore construction becomes evident. Every connection point, the mating surfaces, must align within a margin of error that is almost microscopic, despite the massive shifting of the modules under the wind. This phase of construction is the ultimate test of the planning that preceded it. Once the module is secured, the hookup phase begins, integrating the new arrival into the existing structure to create a unified, functioning whole. It is a moment of industrial transition, the transformation of individual components into a single, cohesive entity. This is the birth of an industrial entity, ready to conquer the deep. The structural integrity of these connections ensures that the platform can withstand the brutal, unrelenting cycle of oceanic stress for decades. There is no room for compromise. Everything is measured, tested, and verified. When you observe this process, you are seeing the culmination of thousands of engineering hours, a testament to human ingenuity that refuses to be limited by the depth of the ocean. It is the final victory of logic and physics over the chaotic, unforgiving nature of the high seas. The creation phase is just the beginning. Now comes the most challenging part of the project, positioning the modules in the open sea. This is the final test of precision before this masterful device officially goes into operation. Let's see how the engineers conquer the ocean during the fusion phase. The loadout operation is perhaps the most nerve-wracking phase in the entire construction lifecycle. You are moving a structure that weighs more than a heavy cruiser from the safety of the fabrication quay onto a specialized heavy transport vessel. This is not just a logistical maneuver, it is a calculated risk against the laws of physics. The stability of the vessel must be perfectly matched to the increasing load of the topside module. Engineers use complex ballast systems, pumping thousands of tons of water in real time, to ensure the deck remains perfectly level as the weight transfers from land to sea. A single miscalculation in the tide levels or the hydraulic timing could lead to structural torsion that would compromise the entire multi-million-dollar asset. It is a slow, methodical, and incredibly tense dance of steel and water, where the objective is to maintain perfect equilibrium while shifting the center of gravity of a massive industrial object. Every second of this process is monitored to ensure the vessel doesn't capsize under the immense, shifting weight of the topside. The leg mating unit acts as a high-pressure, shock-absorbing bridge critical for topside installation. As the transport vessel aligns with the subsea jacket, these units function as giant cushions, neutralizing kinetic energy from ocean swells. During ballasting, the massive weight transfers from ship to jacket in a high-stakes mid-ocean docking maneuver. Achieving millimeter-level alignment is essential. Any deviation risks the entire platform's structural integrity. This brilliant display of mechanical resilience transforms a potentially violent collision into a stable, permanent connection, ensuring the platform's survival. Heavy lift operations showcase a striking contrast. Massive, multi-thousand-ton steel modules moved with the surgical grace of a delicate tool. Crane operators must counteract unpredictable winds and ocean swells, fighting both immense weight and constant motion. This phase is a demonstration of mechanical superiority, requiring nerves of steel to guide structures onto precise mounting points. It is the ultimate collision of brute force and refined engineering, where every lift must land perfectly to avoid structural stress, transforming raw power into architectural stability in the open sea. The boat core field floatover technique is a masterclass in hydraulic control. Unlike crane lifts, the floatover utilizes the vessel's own buoyancy to slot the topside into position. As the transport barge enters the jacket's interior, the engineering precision required is extreme. The vessel must navigate within centimeters of the structure. By adjusting ballast systems, the topside is seamlessly handed off from the barge to the jacket. This logic, floating rather than lifting, is a symphony of naval architecture and hydraulics. It is a high-stakes, permanent installation, where failure is not an option, ensuring the platform remains fixed and operational against decades of harsh maritime conditions. The installation of the Johan Sverdrup Topside by the pioneering Spirit represents a monumental shift in offshore engineering. When dealing with structures of this magnitude, traditional crane lifts often reach their mechanical limits. Instead, this operation utilizes a sophisticated float-over technique, turning the vessel itself into the ultimate tool. As the pioneering Spirit approaches the installation site, the precision required is nothing short of surgical. The massive topside module, weighing tens of thousands of tons, is guided into position between the vessel's twin hulls. Here, the ocean, usually a force of chaos, becomes a managed variable. Through an intricate symphony of hydraulic systems and ballast control, the vessel stabilizes the module against the constant swell. The handoff is the defining moment. As the module is lowered onto the waiting jacket, the margin for error is measured in millimeters. It is a high-stakes transition where engineering logic overcomes the sheer, unrelenting power of the North Sea. By eliminating the need for complex, failure-prone rigging, the pioneering Spirit transforms a potentially hazardous assembly into a controlled, fluid process. This is more than just construction. It is a display of mechanical audacity, proving that when human ingenuity is paired with a vessel of this scale, the deepest and most hostile waters become a mastered workspace. The result is a seamless integration, securing a vital piece of energy infrastructure that will stand firm against the elements for decades to come. This phase represents the core of offshore construction, the sequential integration of the foundation and the superstructure. The process begins with the installation of the foundation, the base anchoring the entire structure to the seabed. Once the foundation is secured by precise pile driving, the focus shifts to the installation of the superstructure. This is when the brain of the rig, the processing modules and control systems, is placed into the foundation. The installation method shown here illustrates the need for synchronization between the transport barge and the heavy-duty crane. The foundation provides structural stability, while the superstructure provides operational capability. Together, they form an industrial unit. Achieving this integration in the ocean requires continuous monitoring of structural stresses and environmental loads. Every bolt tightened and every weld made during this installation is a calculated step toward creating a lasting asset. It was a grueling, multi-stage process with virtually no room for error, requiring absolute coordination between naval architects, heavy crane operators, and structural engineers to ensure the rig was ready for operation. The next decade of service. Once the superstructure was perfectly fixed to its base, the drilling rig now took on the form of a colossal entity. However, to create a complete energy fortress, the work didn't stop at its installation site. We must look back at the arduous journey that brought it there, a legacy journey across the ocean. From the bustling docks of shipyards in Asia, this massive steel structure had to undertake an extraordinary migration to reach its final drilling location in the Gulf of Mexico, or the North Sea. This is not just a story of maritime activity, but of conquering the oceans through the most daring transportation techniques. The launch of an offshore jackup rig is the ultimate validation of naval architecture. As the massive steel hull meets the water for the first time, hydrostatic pressure and buoyancy forces engage in an immediate, high-stakes battle. This process is not just about gravity. It is a calculated descent where engineers monitor every degree of tilt. The hull must remain perfectly level to avoid structural torsion, which could compromise the entire vessel's integrity before it even begins its mission. Once afloat, the rig becomes a self-contained island where weight distribution is managed by an intricate system of ballast tanks. This moment serves as the birth of the rig as a floating asset, moving from the static safety of the shipyard quay into the dynamic, unforgiving environment of the open sea. It is a transition where pure design theory meets the physical reality of the ocean, requiring flawless execution to ensure the rig stays upright and stable for its inaugural journey. Once afloat, the jackup rig must prove its most critical capability, the ability to elevate its hull above the wave zone. The Haven Jackup test is the rigorous trial of the jacking system, a series of hydraulic pins and heavy-duty electric motors that grip the massive steel legs. During this phase, engineers push the system to its limit, ensuring that every rack and pinion assembly can handle the load of the hull without slipping. A failure in this system during an actual operation would be catastrophic, so this test is performed with absolute scrutiny. It is a demonstration of mechanical dominance, proving that the rig is not merely a barge, but a precision machine capable of transforming itself into a stable, fixed platform in the middle of a turbulent sea, ready for the drilling phase that lies ahead. Relocating a jackup rig is a complex multi-phase operation. First, the massive legs must be fully retracted to lower the center of gravity, ensuring stability during the tow. The animation highlights the critical importance of route planning and identifying safe weather windows, as the rig remains highly vulnerable during leg extraction. Navigating narrow lanes requires sub-meter accuracy to avoid seabed obstructions. It is a masterful display of logistics, where every movement is calculated against tide, current, and wind. This precision protects a multi-billion-dollar asset, ensuring a safe, efficient transition from one drilling site to the next. The Floatover installation of the Topside is a masterclass in structural integration. Using vessel buoyancy rather than brute force, this technique precisely slots the topside onto its jacket. As the vessel maneuvers, the margin for error is mere centimeters, requiring extreme stability against tidal currents and swells. Once aligned, ballasting transfers the massive weight onto the jacket. It is a symphony of hydraulics and naval architecture, allowing for the installation of modules too heavy for cranes, proving that intelligence often beats raw power. Transporting two semi-submersible rigs on a single heavy-lift vessel is a masterclass in logistics. Using the dry tow method, The vessel submerges to float the rigs into position before lifting them clear of the water. This shields these massive assets from corrosive saltwater and hydrodynamic drag during transoceanic crossings. Teams must precisely calculate the combined center of gravity to ensure stability throughout the journey. It is a stunning display of engineering capability, treating these giant production hubs as delicate freight to be delivered safely to the world's most demanding deepwater frontiers. The Scarabeo 9 is a marvel of deepwater drilling, utilizing dynamic positioning rather than traditional anchors. Its advanced thrusters and satellite arrays actively counteract winds and currents, allowing the rig to fly in place. Supported by optimized material handling systems for essential drilling fluids, this rig is a triumph of digital and mechanical engineering. By constantly adapting to the environment, the Scarabeo 9 turns previously inaccessible depths into productive, stable workplaces, showcasing our ability to master the world's most challenging offshore frontiers. The transit from Korea to the Gulf of Mexico is the ultimate test for any offshore platform. When a super typhoon intersects with a massive transport mission, there is no place to hide. The platform must be engineered to survive the unrelenting impact. During this harrowing journey, the sea fastening, those heavy-duty steel structures that bind the platform to the barge, undergoes its most extreme, real-world stress test. We are talking about enduring mountainous 15-meter waves that slam into the steel structure with thousands of tons of raw, unbridled kinetic energy. The survival strategy is entirely dependent on the platform's precise center of gravity and the sheer structural integrity of the steel bonds holding it to the transport vessel. Every metallic creak echoing through the hull, every violent surge of the barge against a towering swell, is a direct, aggressive challenge from nature. Successfully weathering a super typhoon during transit is never merely about luck. It is a rigorous validation of every individual weld, every structural bolt, and every complex stability calculation performed during the initial design phase. This journey transforms abstract blueprints into a tangible trial of durability. When the storm clouds break and the vessel remains anchored to its transport, it proves that human ingenuity can indeed stand firm against the most violent atmospheric forces on Earth. It is a quiet triumph of planning, where the margin for error is non-existent and the consequences of failure are catastrophic. Ultimately, this transit confirms that our most ambitious offshore assets are not just built to work, but built to withstand the very worst the ocean and sky can possibly unleash, ensuring the security of energy infrastructure across the globe. The single-point mooring system is an elegant solution to the challenge of anchoring massive tankers in open water. Unlike a traditional dock, the SPM allows a vessel to weather vane, essentially rotating 360 degrees around a single buoy to face the prevailing wind, current, and waves. This passive orientation significantly reduces the mooring forces acting on the vessel's hull, as the ship always presents its most hydrodynamic profile to the sea. By using a swivel mechanism within the buoy, we maintain a leak-proof pipeline connection even as the ship rotates. It is a brilliant integration of naval architecture and fluid logistics, enabling safe and efficient offshore loading operations in conditions that would make fixed berth docking dangerous or impossible. Installing a massive jacket structure on the seafloor is a high-stakes landing maneuver. To achieve the sub-millimeter precision required, we rely on a suite of high-tech installation aids. Pile grippers hold the jacket perfectly vertical, while the piles are driven into the seabed, acting as a temporary mechanical clamp that resists the sway of the ocean. Diaphragm closures and grout seals are equally critical. They prevent the seabed sediment from entering the pile sleeves, ensuring that the structural integrity of the pile-to-jacket connection is not compromised. Finally, the grout packer is activated to create a pressurized seal, allowing high-strength cement grout to be injected into the annulus between the pile and the jacket sleeve. This sequence transforms the jacket from a loose, temporary assembly into a permanent, monolithic structure capable of supporting thousands of tons of topside load for decades. After nearly half a century standing firm against the North Sea's fury, the Brent Charlie platform, the heaviest and largest of the iconic Brent field, has finally been brought home. This monumental decommissioning project represents the closing chapter of a 50-year legacy that contributed over £20 billion to the UK economy. Dismantling Charlie was never going to be simple. It was the toughest saved for last, a unique engineering challenge that tested the limits of Shell's decommissioning team. Unlike its predecessors, Delta, Bravo, and Alpha, Charlie presented a complex structural nightmare. Its 40 external conductors were exposed directly to decades of harsh winter storms, necessitating a delicate, bespoke strategy. To ensure stability, the team opted to cut weaker conductors underwater while strengthening others for above-surface removal. The legs themselves were packed with process equipment, requiring the team to climb deep inside narrow columns to execute precision cuts using high-pressure, abrasive water jets. By employing castellation cuts, a castle-shaped locking pattern, the engineers ensured the platform remained perfectly stable during every stage of the separation process. The climax of the operation was the record-breaking lift by the pioneering Spirit. As the world's largest construction vessel, it was the only machine capable of removing the 31,000-ton topsides in a single, seamless maneuver. Because Brent Charlie was 80 meters wide, the largest in the field, the vessel itself had to be widened to fit around the platform's legs. When the final, total platform shutdown TPS switch was flipped, it was a deeply emotional moment for a crew who had treated this platform as a home from home for decades. Watching the platform sleep as the last person departed was the end of an era. The final transit into Abel Seton Port was a masterclass in sub-millimeter precision. Maneuvered into the quay within a tight 4.5-hour tidal window, the platform was rolled on shore at just 15 meters per hour using 40 hydraulic push-pull units. Now grounded on land for the first time in 5 decades, Charlie is being systematically dismantled for recycling. This project was more than just engineering. It was a testament to the talent, resilience, and skills of the North Sea workforce. As the giant is reduced to scrap, those involved feel a mix of pride and nostalgia. Brent Charlie may be leaving the ocean, but the skills and spirit of the people who maintained it remain a national asset, ready to power the future as the UK transitions toward a net zero horizon. Mooring Shell's Prelude, the largest floating facility ever constructed, requires a system of unprecedented scale and strength. Because of its massive size, Prelude cannot rely on a standard anchor chain system. It utilizes a specialized turret mooring configuration that allows the entire 488-meter-long vessel to rotate in response to the environment. The mooring lines consist of massive chains and polyester ropes designed to withstand the extreme forces of the cyclone-prone waters off Western Australia. The installation of these lines is a feat in itself, requiring heavy-duty anchor handling vessels to navigate the precise layout required to maintain the vessel's position over the subsea wellheads. The tension in these lines is managed by a sophisticated control system that ensures the facility remains stable, even during severe weather events. This is offshore engineering at its absolute limit, providing a secure, reliable foundation for a floating industrial city that must operate safely in one of the world's most demanding maritime environments. The maintenance of offshore assets requires a specialized approach known as IRM, inspection, repair, and maintenance. Because these facilities operate in one of the world's most corrosive environments, continuous vigilance is mandatory. This segment highlights the use of advanced remotely operated vehicles and specialized diving teams to perform subsea integrity checks on jacket structures, risers, and mooring lines. We are constantly monitoring for signs of cathodic protection, failure, fatigue cracking, and biofouling. If a defect is found, the IRM team executes a precision repair. Whether it involves subsea welding, clamping a structural member, or replacing a failed valve on a subsea tree. This continuous cycle of inspection and intervention ensures that the platform's health remains optimal, extending the operational life of the field significantly beyond its original design life. It is the invisible but critical work that guarantees the safety of the crew, the protection of the marine environment, and the reliability of global energy production. The vessel is now secured, coordinates locked, and a fortress-like foundation established in the middle of the ocean. Stability is the prerequisite. The ultimate objective remains thousands of meters beneath the waves. Having mastered the art of standing firm against the elements, the focus shifts from the hull stability to the subsea wellhead, the gateway to the reservoir. This transition demands absolute mechanical precision, utilizing the blowout preventer as the final line of defense against subsea catastrophes and remotely operated vehicles to navigate the crushing depths. From the surface to the seafloor, the operation initiates the drill, connecting the reservoir to the world while sustaining the high-pressure life of the engineers on board. Drilling a deepwater well is a complex, years-long endeavor that transforms geological theory into energy reality. After seismic surveys identify a reservoir deep beneath the seafloor, engineers determine the safest drilling path. Whether operating from a drill ship, a semi-submersible, or a production platform, the process relies on a massive hoisting system, high-pressure pumps, and a critical blowout preventer, BOP stack. The journey begins by spudding in. To stabilize the soft seabed, a large diameter base pipe is jetted into the sediment. Once anchored, drilling commences. The drill bit rotates at the end of a long drill string, while drilling mud, a sophisticated, environmentally friendly mixture, is pumped down to circulate back to the surface. This fluid is the lifeblood of the operation. It lifts rock cuttings, lubricates the bit, and exerts hydrostatic pressure to prevent underground fluids from entering the wellbore. As the hole deepens, the team periodically pulls the bit to install casing strings. These are cemented into place, creating a permanent, pressure-tight steel barrier against the surrounding rock. Once the depth reaches areas where reservoir pressures increase, the BOP stack is installed at the seafloor. This massive array of valves and rams acts as the ultimate safety net, capable of sealing the well instantly if unexpected pressure surges occur. When the target zone is reached and resources are confirmed, a final casing string is installed to secure the reservoir. This meticulous process, from the initial jetting of the base pipe to the final cement job, ensures that the well is not just a hole, but a safe, durable conduit ready for decades of productive energy extraction. In deep-water environments, HD footage from Oceaneering's ROVs is vital for maintaining rig integrity. These high-resolution cameras allow engineers to inspect subsea structures at extreme depths, detecting corrosion or structural cracks invisible to the naked eye. Serving as the eyes of the system, these visuals enable immediate intervention against anomalies, ensuring absolute safety before minor defects escalate into catastrophic failures. Remote inspections using deep trekker technology revolutionize rig maintenance. By replacing human divers with compact, maneuverable vehicles, engineering teams can safely navigate tight jacket structures or pipelines. These devices collect critical data on metal thickness, coating conditions, and weld integrity. This cost-optimized solution enables continuous operations, verifying structural health, and performing essential maintenance without the downtime required for manual inspections, effectively ensuring safety and efficiency in the most challenging underwater environments. Installing riser systems in ultra-deep waters, such as the projects in Brazil, is an engineering feat. This method utilizes flexible pipe-lay technology, a solution designed to withstand pressure and depth extremes that traditional rigid pipes cannot endure. These risers function as the arteries, connecting the floating production unit to the subsea wellhead. In deep-water environments, these lines must support massive loads from currents and their own weight. The flexible pipeline method from specialized vessels ensures the pipe is neither twisted nor deformed during deployment, protecting the internal structural layers. This technique is essential for extracting oil in the world's most demanding environments while maintaining the necessary flexibility for the floating vessel. Maritime developments provide specialized pipe deployment and recovery technology for the offshore sector. This footage focuses on the versatility of their pipe tensioner and reel drive systems, specifically engineered for subsea installation projects. A core advantage of this technology is its ability to maintain precise tension control while deploying risers to the seafloor. Any fluctuation in tension could lead to catastrophic structural damage to the pipe. With MDL's automated control systems, speed and tension are regulated with extreme precision, allowing engineering teams to operate stably even in unfavorable weather conditions. This accuracy is a critical factor in maintaining the stability of the rig while continuous subsea operations are underway, ensuring the connection between the rig and the seafloor remains uninterrupted. The decommissioning of the Ninian Northern Jacket by Allsea's pioneering spirit is a testament to the transformative capability of reverse installation. Rather than relying on traditional, dangerous underwater cutting methods that pose significant environmental risks, this heavy-lift vessel utilizes motion-compensated lift beams to remove the massive 100-ton jacket structure from the seabed in a single, fluid motion. The footage captures the immense mechanical power required to maintain stability for such a colossal structure while hoisting it safely to the surface. This operation demands that engineers calculate the dynamic center of gravity for a jacket that has been subjected to decades of marine growth, structural fatigue, and relentless corrosion. Once clear of the water, the jacket lift system secures the structure in a near-vertical position, effectively eliminating the need for complex sea fastening or additional support barges during transit. This is far more than a simple removal. It is a sophisticated engineering campaign specifically designed to restore the seabed with surgical precision. By delivering the jacket intact to the recycling facility, the operation achieves a 98% steel reuse rate, demonstrating the industry's unwavering commitment to environmental responsibility and sustainable resource management at the end of an asset's lifecycle. This success proves that even the most massive industrial challenges can be managed through innovative, integrated technologies. By setting a new global benchmark for safety and efficiency, the pioneering spirit confirms that the future of offshore decommissioning lies in smarter, total solution approaches that prioritize seabed health while delivering long-term value to the global energy infrastructure. From the first spark of a weld in a distant shipyard to the final, rhythmic extraction from the deep-sea reservoir, we have witnessed the ultimate triumph of human ingenuity. We have successfully spanned the chasm between the surface and the abyss, transforming the most volatile and unforgiving ocean into a controlled, precise theater of production. The Steel Island now stands as a testament to our reach, an unshakable fortress that quietly fuels the world from the darkness of the seafloor. The long voyage is complete. The well is secured, and the steady pulse of the rig continues, enduring and relentless, deep beneath the crushing waves. Mission accomplished.